All right, so I wanted to share something with you. I love my quotes, and so here's one. I know sometimes you feel all alone, but you always got a friend there. So, just thought I'd like to start that off right there. All right, so today, implicit differentiation. Been uh, giving this some talk up. Been talking this up for our last differentiation. Okay, so. I've been talking this up for a little bit here, and so wanted to. It's finally time for us to get there, get it, and have it as one of our tools. So this one here is mainly used for non-functions. Okay, but sometimes the problems will be as functions, and they'll just have things like this. But mainly, it's used for non-functions. It can be used for functions, though. But the idea. So the main idea for this is that the x's and y's these things are going to be mixed up, okay? Well, what I mean by that is, what we've been doing has been called explicit differentiation, not like the, you know, the so-called lyrics that the so-called music that y'all listen to, but explicit is the way. What it means is that y is written and there's only x on one side, like 3x squared sine of x or whatever, so this is an explicit function because you have the x's are mixed in together. Implicit, so x's, only x's. Implicit, the way this would go would be like 3 equals y squared sine of x. Implicit, so you can see the differences right here. The x's are the only thing over here, but over here we have the y's and the x's all mixed up. So with this, there are ways you can go around. Sometimes, like on this one, it wouldn't be too bad to actually solve this function for y, and go from there and do it explicitly. But sometimes though it's not going to be that easy to do. In this case, it wouldn't be that bad. But so here we go. So explicit, of course, with this one we'd have to use the product rule on this, and so we'd say dy over dx equals 6x sine of x plus 3x squared cosine of x. Okay, and so we'd have that. Not bad. All right, this one here. Well, the derivative of 3, well, that's just so what we're going to do is we're going to, let's just write it out like this. So we're going to do the derivative of both sides, d over dx of 3, and we're doing the derivative with respect to x. So what it says with respect to x, meaning the x is in the denominator right there. And whatever you do to the left side, you got to do that to the right side as well. And so then we have y squared sine of x. That's how this works out. All right, so in this particular case, these are still being multiplied together. So we're still going to end up doing the product rule on that side. But over here, we have dy over dx equals 3. Well, derivative of 3 is 0. So over here, though, now what we're going to do is we still have to use, like I said, we still have to use the product rule. So, if we did f, okay, that's fine, times g prime, cosine of x. All right, plus, all right, g, now times the derivative of f. Okay, well, if it was, okay, not a big deal, but it's 2y is usually what we would go with. However, here's a special thing, okay? This is what separates implicit differentiation. Being is that this y is not x, we're taking the derivative with respect to x, we need to include dy over dx. is what we need to include in this. And so now we have our problem set up like this. So if we were to go through and try to solve for dy over dx, well, then we'd end up with negative dy over dx, if we move this over to the other side, times 2y sine of x equals y squared cosine of x, and then we could divide, and we'd have dy over dx equals negative y squared cosine of x over 2y sine of x. And then, of course, you could, if we wanted to, we could also write this as negative 1/2 y squared divided by y is y, cosine of x divided by sine of x is cotangent of x. And so it's kind of a weird way of going about this, and a lot of times people have a hard time adjusting to that weirdness, but it's not something that we need to really freak out about. It's something impossible to deal with. So just some things that as being there with you. Okay, so let's take a look at another one. And then again, like I said, we tend to use these for non functions. Like here's one: x squared plus y squared equals 1. Not a function, but very important equation. What is this the equation for? This is the equation for the unit circle. This equation gives us the unit circle right there, because that's a cosine and that's a sine. Cosine squared plus sine squared is 1. That's where that Pythagorean identity comes from. Cosine squared theta plus sine squared theta equals 1. Sine is your y, cosine is your x. There you go. That's what ties it all in together. This is the units, and so everything comes together because of this right here. Now, with that then, all right, so we would go through, okay, and if we want to take the derivative of both sides, so d over dx of this and d over dx of the 1, okay, what's the derivative of 1? Well, it's still 0. That hasn't changed. All right, derivative of x squared is going to be 2x plus, and then we have the derivative of y squared. Well, it's going to be 2y, but y is not the same as x, so that means we have to have dy over dx every single time. Okay, and then we could solve for dy over dx, because a lot of times what it's going to say is the directions will say find dy over dx. That's what they'll say, find dy over dx. So you got to take the derivative, okay? Then we got to solve for dy over dx. So we minus 2x from both sides. So we have 2y dy over dx equals negative 2x divided by 2y divided by 2y. And so dy over dx equals negative x over y. And this would be that would tell us the slope at any point on the unit circle. If you plug in the x and the y from the unit circle, you'll get it. So yeah, which is pretty neat, I think. Okay, so let's take a look at maybe another one. Sometimes so just kind of got to be ready for things that they could pop up. How about y equals the sine of xy? There we go. This looks like it could be a scary one. All right, so here we go. All right, again, we have to take the derivative of all this. So we're going to take the derivative with respect to x. So again, let's say find dy over dx, be the directions, find dy over dx. So we do, and that's what we're going to start off with. We're just going to be doing implicit differentiation. So this one's going to be dy over dx on this side. Okay, if you want to call it 1 dy over dx, you're thinking, hey, that's derivative y is 1, then okay, 1. But y is not x, we need that dy over dx. Over here, the derivative sine of something is going to be the cosine of that something, times, then we got to take the derivative of that something. Well, that something, what do we need to use? Product rule. So now we have, all right, f times g prime, so x, derivative of y, we already talked about that, is dy over dx, plus 1y. Okay, now we're like, all right. So we got to get the dy over dx's together, and now we get to do all sorts of algebraic acrobatics to do so. because what we're going to have is we're going to have x dy over dx cosine of xy, if we distribute the cosine of xy into here, plus y cosine of xy. And so then we'd say, okay, well then this would be, we subtract this from both sides, x dy over dx, cosine of xy, x dy over dx, cosine of xy. So both of these now have dy over dx in, so that means I could factor that out, dy over dx. If I factor dy over dx out of the top one, I get 1. And then we have minus y cosine of xy. Oh, I'm sorry, x cosine of xy, sorry. It's a little sloppy. Sloppy. All right, and then y cosine of xy. And then we can divide and get dy over dx equals y over y of cosine, y times cosine of xy over 1 minus x cosine of xy. Okay, cannot divide those because this one is included with that 1, so we can't separate them, and this would be our answer. And yeah, it doesn't look pretty, but it really wasn't a pretty problem to begin with. So just some things that we kind of have to be ready for, and it's a kind of a big mess. So in addition to this, we might also sometimes want the second derivative, which would be d squared y over dx squared is what we might want. And so let's say we go back to that unit circle 1, x squared plus y squared equals 1. Before you get the second derivative, we need to have the first derivative. So the first derivative we already did on the other, earlier, a few minutes ago. And we said dy over dx equals negative y over x is how that worked out. Okay. Negative x over y. All right, so we did that one already. So we had negative x over y. And so now we want to take the derivative again on this one. So we would do the derivative, d over dx, both sides. Okay? That would give us d squared y over dx squared equals, and then we do the bottom times the derivative of the top minus the top times the derivative of the bottom, which is dy over dx, all over the bottom squared. All right, this gives us then negative y plus x dy over dx over y squared. Well, that's nice and all if you knew what dy and dx were, but we don't all the time. And so actually what we want to do is we want to take this and put this on terms of x and y. Well, dy over dx, what should we do with that? We found the derivative earlier. It was negative x over y. We already found that derivative. We know what dy over dx is. So we're going to substitute that in. So we'll have negative y plus x times negative x over y all over y squared. All right, cool. So now we're cooking. All right. So we're going to bring this around town. Okay. Both of these have a negative, so we can factor out a negative. That's going to be y over 1 because we have fractions. This is going to be plus x squared over y all over y squared. So all I did was do x times x, get x squared, factor out this negative, factor out that negative on the outside. Well, to add these, I need a common denominator. So the easiest way to do that is just to multiply this one by y over y, obviously. And so we'd have negative y squared plus x squared over y squared. Well, that's, of course, is y squared over 1. So then, I'm going to flip that over. Well, no, let's just do it. So we'd have y here, right, times 1 over y squared, which gives us y cubed. Okay, we have that negative. And normally we like the x's to be in the front, x squared plus y squared. But what does x squared plus y squared equal? We were told from the very beginning x squared plus y squared equals 1 in this problem. Now, sometimes they might use 25 or 16 or some other square. And so what this means is in this particular problem, throughout this entire problem, this is all we care about. That means that this x squared plus y squared, that's 1. So we have negative 1 times 1, and we end up with negative 1. And so it's really interesting the way that this all plays out here. So sometimes this is where we're going to be, but that's kind of the key. When we find the second derivative, what we do is when we get that dy over dx, we substitute back in the derivative function, or the derivative equation. Let's put it that, because that might not be a function either. In this case it is, but sometimes it's not. So yeah. All right, so just wanted to throw that at you and see what you think. And yeah, so mainly we got to follow all those rules, because those rules are not, again, those rules are not guidelines. Those are the rules. This is what you have to use. Chain rule, product rule, quotient rule, power rule. You have to use them. But now, if you take the derivative of y, that means you have to include dy over dx at that point. Technically, too, if you wanted to do it every single time, dx over dx, well, dx over dx is just 1, because that's the rate of change of x with respect to x. That means every time x goes up 1, x goes up 1. So yeah, obviously it's up 1 over 1. So, but if that's really confusing for you, then don't even bother with it. But sometimes people wonder. So just want to let you know about that. All right. I'm going to get some problems coming at you, so I want you to try them and see what you can come up with, and do the best you can. All right. At this point, maybe you won't, but just in case, are there any questions? Yeah, later on we'll talk about application. But right now, we're just going to practice doing some of these. Okay.